Hello students, welcome to all of you to the class number 5 of chemical bonding. And in this chapter, the previous class, I have told you about the overlapping of half-filled atomic orbitals. Atomic orbitals, that means half-filled atomic orbitals, overlaps in two ways I have told you. One is head-on overlapping that occurs between the half-filled atomic orbitals of respective atoms along the internuclear axis, so that the extent of overlapping was found to be maximum and the bonding electron pairs present at the overlapping region antiparallel to each other. That was the concept behind sigma bond. And half-filled atomic orbitals also overlaps with each other in some different way that I have told you, that is called lateral overlapping or sidewise overlapping, little bit of weak as compared to that of a sigma bond. And due to such sidewise interaction of half-filled atomic orbitals, the bond which was formed known as your pi bond, and this pi bond is very weak than compared to sigma bond, I have told you. Is that clear? So little bit of information I need to provide over here regarding the overlapping of atomic orbitals. One was overlapping of atomic orbitals. Atomic orbitals, it occurs mainly in two ways. First category, that was by head-on overlapping of half-filled atomic orbitals. Half-filled atomic orbitals. Okay, so overlapping of head-on overlapping of atomic orbitals leads to the formation of sigma bond. Sigma bond, or it is designated as this, like this, sigma bond. And sigma bond particularly formed, I think I have told you in my previous class, due to first one, that is SS overlapping. SS overlapping of half-filled atomic orbitals. This can be represented like this. This one is one half-filled s orbitals get overlaps with another half-filled s orbital. These are s orbitals. One s orbital. This one is another s orbital, and this axis is called its internuclear axis. Then overlapping in this manner, if they have two electrons lying anti-parallel to each other, these two electrons present at the middle, that is at overlapping position. So this is the overlapping of s orbitals leading to the formation of sigma bond. So this one becomes, its molecular orbital is like this, I have told you. This one, this is its molecular orbitals. Molecular orbital, or you can say sigma molecular orbital. That clear? Next, second type that I have told you, sp overlapping. Sp overlapping. One s orbital, then this one is one p orbital, same orientation along same internuclear axis you see. Then the head-on overlapping is possible over here. This is S and this one is P. This is SP overlapping. SP overlapping. And electrons are present at the overlapping region. This is SP sigma bond, you can see here. This one is called SS sigma bond. Okay, and here this sigma bond is known as SP sigma bond. SP sigma bond. And the molecular orbital shape, since this is overlapping region, the probability of getting electron is maximum within this overlapping region. So it can be done like this one and this one. This is sp overlapping of this is molecular orbital. You can say this one is your molecular orbital. That clear? And the final one, that is pp overlapping. pp overlapping. Here also sigma bond formation possible. This one is one p orbital, half filled p orbital. and another half filled p orbital you can do like this, antiparallel electrons here, one electron like this, and due to pp overlapping, this is again your internuclear axis. Is that clear? So overlapping will be like this. Due to lack of space I am doing over here, just imagine, just manage it. So this is pp overlapping, pp head on overlapping you can say, that will be better, and lead to the formation of pp sigma bond, pp sigma bond. So here the molecular orbital can be, since the middle portion is the overlapping region where you can get the probability of electron density maximum over here, so its molecular orbital shape can be like this. This one is your internuclear axis and this is its molecular orbital you can say, because molecule formation already being there, molecular orbital. So sigma bond can be formed due to overlapping of such half-filled atomic orbitals in this following manner, that is due to SS overlapping, SP and PP overlapping of atomic orbitals. That clear? Okay. So now let us consider the formation of a pi bond, how it occurs, particularly due to lateral overlapping or sidewise overlapping of a half-filled atomic orbitals. So you see, and it is possible only, I have told you, the p orbitals, half-filled p orbitals having same orientation. Okay, same orientation means, just see, suppose one p orbital is like this, you can write over here, formation of pi bond, formation of pi bond, that is by sidewise overlapping, of half-filled atomic orbitals, half-filled atomic orbitals. Okay, you see, suppose one orbital is, p orbital is like this, I am saying, and it is orienting along, let's say this one is px, x-axis I am considering like this one is x-axis, this axis is your x-axis, or you can say this one is z-axis and this one is your y-axis. Is that clear? So this one is px, this is your z-axis here, this z-axis is your internuclear axis. Okay, this z-axis is your internuclear axis, this axis is your internuclear axis, that is z-axis. Okay, so another atom having half-filled, here the electron can be assigned like this, another p orbital, let's say like this one, again the px orbital of another atom and its electron laying antiparallel like this. So whenever they overlap to each other in this manner, so there exists a sidewise overlapping, you can see this one is sidewise overlap. Okay, so you can say this one is, these are two p orbitals, two half-filled p orbitals, two half-filled p orbitals overlap with one another, with each other laterally. Okay, laterally overlapping is there. So overlapping region is this, here the electron density, two electrons lying antiparallel within this region you can imagine, or this region, no problem. Okay, so due to overlapping, so orbital will be like this one, let me do it like this, because within this region electron densities are formed. That clear? And this z-axis is your nodal plane, this one is your nodal plane. Nodal plane means within this region no electron densities are there, no electron density. Okay, so here this one is called your molecular orbital, pi molecular orbital. So pi bond formation is like this. Is that clear? So with this I need to provide you several examples of this orbital overlapping concept. So let us consider very simply hydrogen molecule, you know, H2 molecule, H having configuration 1s1. So in orbital overlapping concept you can show like this: one half filled orbital of 1s1 of one hydrogen overlaps with 1s1 hydrogen of another atom. These two orbitals overlap to form SS sigma bonds. So this one is nothing but the representation of H2 molecule. H2 molecule, and this bond that is called sigma bond. Clear? Next, if I represent the HF molecule, hydrogen fluoride molecule, how it is formed, beta? So hydrogen having configuration 1, so that is 1s1 half filled 1s orbital. And if I consider the fluorine 9, 1s2, 2s2 and 2p5, I can represent like 2px, 2py, 2pz, 1 1 1 2 2. So that will be 2 2 1. Okay. So fluorine configuration like this. So you have to consider the half filled atomic orbitals. Here that is 1s1 and another one is this is 2pz1. Okay. So s orbital is spherical symmetry in shape. So this one is half filled 1s1 of hydrogen, and take this p orbital, this pz orbital, because this one is going to overlap along internuclear axis. Okay. So forget about other orbitals. So if I consider 2pz of fluorine, so this one is 2pz of fluorine of F atom, fluorine atom. So it's a unpaired electron like this. So this is the formation of HF molecule, HF molecule, HF molecule, and its molecular orbital diagram can be like this and this one. Okay, so this is HF molecule. Clear? Next, if I consider Cl2 molecule or F2 molecule, let's say F2 molecule, F2 molecule. So two fluorine atoms having two half filled 2pz orbitals. So it will be like this, and this 2px, 2py, it remain as such. So just consider this 2pz. I am considering 2pz of one fluorine atom. Its electron like this, and this is my internuclear axis, z axis, and another p orbital like this. It is also unpaired electron like this. So as a result of overlapping, what happens? You see here, this is the formation of F2 molecule. F2 molecule. This is the formation of a F2 molecule. Overlapping of two half filled pz orbitals. Clear? So with this, if I consider O2 molecule, let's say O2 molecule, what will be its Lewis structure, beta? So oxygen, double bond oxygen, and two lone pairs of electron. Each oxygen atom has two lone pair of electrons. This is the structure of a O2 molecule. So be remember, whenever a double bond is there, one is formed due to head-on overlapping, that is called sigma, and another one that is due to lateral overlapping, that is pi. Is that clear? So let us discuss how by orbital overlapping concept. Oxygen having configuration 8. 8 means 1s2, 2s2, 2px, 2py, 2pz. So oxygen 8 electrons. So 2 to 4, 5, 6, 7, 8. So here that will be 2 and 1 and 1. 2py, 2pz having 1. So just like consider two oxygen atoms are approaching towards themselves. So what happens if I represent for one oxygen atom 2px, 2py, 2pz? Okay. So this one is one oxygen atom having this one is 1p lobe and this one is 1p lobe. Okay. So this one is 2pz. This is its internuclear axis, I am saying. So this 2pz, this one is 2py and this one is 2px. So 2pz having one unpaired electron, 2py having one unpaired electron, and 2px, that is two electrons are there. So here this one is its valence shell, second orbit. This is its valence shell. So now let us discuss how actually here 2px having two unpaired electrons. We forget about that. So let us focus about its formation, bond formation. Okay. So another oxygen atoms having this one pz, 2pz having electron like this. This one is 2px and this one is 2py. 2py. That clear? This is 2pz. So after overlapping, what happens? You just see. So this side becomes minimum, and here the overlapping is like this. 2pz orbitals overlaps, and 2px remain as such. 2px remain as such, and 2py having also unpaired electron. So here this is for this one is your pp sigma bond. pp sigma bond, because this bond is formed by head-on overlapping. By head-on overlapping. Okay, and here you see this one and this one. Is that clear? Here also electron remains antiparallel. So what about this? 2py, 2py. They are lying just parallel to each other. So there is formation of sidewise overlapping, and this case also possible from here to here. It does not mean that only the overlapping will occur at the above the sigma plane, but rather below also. Okay, chance of formation sidewise overlapping of above and below. Okay, so that's why oxygen atom having this one is sigma bond O, this one is sigma bond head-on overlapping, and another one is pi bond. This is due to sidewise overlapping. And here you see this 2 electron, they remain as lone pair. That means they do not formation in, they don't take part in the electron sharing. So the two lone pair electrons like this and like this. So this is the formation of O2 molecule. One is sigma, another one is pi. Like that of you can consider also dinitrogen molecule, N2 molecule. Do its Lewis structure, nitrogen. There exist 3 covalent bonds, and each nitrogen associated with one lone pair. This is its Lewis structure. Okay, so whenever 3 bonds are there, then this central one is sigma bond, and the above one is pi bond, below one is pi bond. 2 pi bonds and 1 sigma bond. So let us discuss how it is possible through orbital overlapping concept. So nitrogen having configuration 7, 1s2, atomic number 7, 2s2, 2px, 2py, 2pz. Each orbital is half filled. So 3 half filled atomic orbitals are there, and this electron, this 2s2, it remains as lone pair, non-bonding electron pair, because this 2s, 2p, 2p all have degenerating orbitals. Degenerate means same energy. Okay, you can't consider this 1s2 because it is fast orbit. Okay, so only valence shell participate in bonding. I have told you at the beginning. So here the formation of a dinitrogen molecule. You can consider one nitrogen. This one is 2p z, 2px, and this one is 2py. Okay, so each having one unpaired electron. This one is 2pz, here 2py and 2px. So another nitrogen molecule, right? Another nitrogen atom. It can be like this. Here this one is your 2pz, 2py, 2px, having unpaired electron. And here the orientation of electron is a little bit of opposite. You can mention here also. Okay, because this one is the overlapping region. This one like this, and this one like this. Okay, so what happens? Overlapping along internuclear axis. So this will be overlapping is like this. Clear? So here this is pp sigma bond, and here this one is formed by lateral overlapping, and also here this is also formed by lateral overlapping. So this one is sigma, this one is pi, this one is pi, and the formation of pi bond may also occur from this side, here to here. Okay, so one sigma bond and 2 pi bonds is lying at the middle. So this is nitrogen, ट्रिपल बॉन्ड नाइट्रोजन, द बीच वाला जो मिडिल वाला ये आप लोग का सिग्मा बॉन्ड हो जाएगा, और ये एबव पाई और बिलो पाई 1 फॉर्मेशन हो जाएगा, और ये जो 2 इलेक्ट्रॉन्स ऑन 2s इट रिमेन एज लोन पेयर. दीज आर लोन पेयर इलेक्ट्रॉन. दैट क्लियर? ओके. So after we have discussed the formation of molecules by means of orbital overlapping concept, and two types of bonds are formed due to orbital overlapping. One you can say sigma bond, another you can say pi bond. So let us discuss the difference between sigma bond and pi bond. Very important, that is difference between sigma bond and pi bond. Difference between sigma bond and pi bond. This one is sigma bond. It is designated like this, and another one is that is pi bond. Okay, so first point you can say a sigma bond is formed due to head-on overlapping of half-filled atomic orbitals. And a pi bond, you know, a pi bond is formed by the sidewise overlapping of half-filled atomic orbitals. Next, a sigma bond is formed. It is formed by SS, SP and PP overlapping of orbitals. Clear? So pi bond only p orbitals. It is formed only by overlapping of p orbitals, or you can say pp sidewise overlapping. Is that clear? Next, the electron cloud is symmetrical about the line joining the nuclei of two atoms. Next, here the electron cloud is unsymmetrical. The electron cloud is unsymmetrical. Okay, and present above and below the internuclear axis. Next, the extent of overlapping is maximum. The extent of overlapping is maximum. That's why a sigma bond is a strong bond. Okay. for which a sigma bond is a strong bond, you can say. Is that clear? So here it is opposite. You can consider there is small overlapping of atomic orbitals, hence a pi bond is a weak bond, A sigma bond is highly stable and less reactive. You can write over here, a pi bond is less stable, you can say, less stable and highly reactive. Next point you can consider, that is free rotation about a sigma bond is possible. So if A and B are attached by means of a single sigma bond, let's say this one is single sigma bond, then you can rotate the molecule through this sigma bond, single sigma bond. Okay, but if there is sigma bond as well as pi bond which is present above this sigma bond, then the rotation becomes restricted. Difficult rotation is there. So you can say over here, rotation is restricted about a pi bond. Another, the sigma electrons are fixed. The electron pairs of sigma bond lies in between the nuclei of two bonded atoms, lies in between the nuclei of two bonded atoms. Next, here, that means it is symmetrical. Okay, electron pairs are exactly at the center between nuclei of two bonded atoms. That's clear. But pi, here you can say the pi electrons are mobile in nature. Okay, the pi electrons are mobile in nature. Mobile means delocalized. That means pi electrons are little bit of a free to move. Okay, since it is formed due to side-wise overlapping of half-filled atomic orbitals. So these are the key points to distinguish between a sigma bond and a pi bond. Next, since we have gained the idea about the formation of a bond, the sigma bond and pi bond in a molecule, so now let us discuss about some bond parameters. Okay, bond characteristics, or you can say bond characteristics, or you can say bond parameters. So bond characteristics or bond characters or bond parameters. So first one, that is I need to say about bond length. So bond length means it is the equilibrium distance between between nuclei of two bonded atoms. That clear? Suppose a homodiatomic molecule I am considering, that is, let's say A2 molecule, I am considering A2 molecule. So here this one is one atom, this one is another atom. So this is its nucleus, these are two nucleus. So this new internuclear distance, this is called bond length. Here this one is called bond length. It is designated as D. So DAA, you can say DAA, that is the bond length of A2 molecule. This is nothing but the internuclear, half of internuclear distance. Okay, you can say 1/2 of internuclear distance. This is the expression for bond length over, since two atoms having equal size. Okay, so bond length I can write over here, bond length that is equal to DAA upon 2. So if heterodiatomic molecule, if I consider, okay, in case of heterodiatomic molecule, different size, heterodiatomic molecule, that means two different molecules are there. Let's say AB I am considering, AB. So this one is, or very simply I can say, let's say HCl molecule. That clear? So this one is hydrogen and this one is chlorine. So each nucleus, this distance is called bond length. And here you can say from here to here, this is radius of hydrogen, half distance you can consider. This one is radius of hydrogen and this one is radius of Cl. So DHCl, the bond length of DHCl, that can be written as radius of hydrogen plus radius of chlorine, since they have different atomic sizes. Is that clear? So D bond length of heterodiatomically AB, that will be radius of A plus radius of B. This is the expression for bond length. Then various factor I am considering affecting the bond length. Various factor, what are these factors? Various factors on which your bond length depend. Various factors affecting bond length. What are these factors? So first one, that is atomic size, obviously. Atomic size. So larger the size of bonding atoms, so more will be distance. Very simple. So larger the size of bonding atoms or bonded atoms, more will be the bond length. Okay, if I consider beta HI, HCl, HBr, HCl and finally HF. You see the bond length decreases since the size of halogen decreases. Okay, the size of halogen decreases, so the bond length also decreases. Next one, after atomic size, another factor that affecting your bond length, that is multiplicity of the bond. Multiplicity of the bond. So multiplicity of the bond means more the bond order. Here you can say triple bond having less bond length than compared to double bond than compared to single bond. That clear? So the bond length of, you can say HC triple bond C alkyne is less than that of carbon double bond in alkene, which is also less than that of saturated hydrocarbon, like this. Okay, so more the bond order, that will be lesser will be the bond length. That clear? Next, third factor, that is hybridization. So we will discuss this term just after this topic. Just remember, if I am considering carbon-carbon bond length, carbon-carbon. Here you see this triple bond, this carbon is sp hybridized. I will tell you this about this hybridization. Okay, let me vanish this point because it will be confusing since I have not taught you about hybridization. Just remember these 2 points on which your bond length depends. Okay, so next parameters I need to discuss over here. Next parameter, important parameter, that is bond enthalpy. Bond enthalpy, or you can say bond energy. Bond energy. So generally, you know, during the formation of a chemical bond, energy is released. The potential energy, net potential energy decreases, or you can say energy is released and the system becomes stable. Okay, so what do you mean by bond energy? That means the amount of energy required to break the bonds. Okay, so during the formation of bond, energy is released. So during the cleavage of a bond, energy is required. So you can write over here the amount of energy, required to break 1 mole of bonds of a particular type into the gaseous atoms is called bond enthalpy. Next, various factors affecting bond enthalpy. So first one, that is size of bonded atoms. So larger the size of bonded atoms, more will be bond length, and a small amount of energy is required to break it. Okay, so larger the size of bonded atoms, more will be the bond length, and less will be the bond energy, or you can say bond dissociation enthalpy. So again, if I consider Hi having bond dissociation enthalpy less than compared to HBr, then less than compared to HCl, less than compared to HF. Okay, so bond energy increases from Hi to HF. Next one, that is a case of hybridization is there. I don't need to confuse you guys because I have not discussed the topic hybridization. So next one, that is, can consider lone pair electrons. So more the number of lone pair electrons over the bonded atoms, more will be the repulsion, and hence bond enthalpy becomes minimum. Okay, that means if number of lone pair electrons are there, you see, if I consider a molecule like AA, if number of lone pair is maximum, then what happens, this lone pair and bond pair trying to repel one another. As a result, this bond can be easily broken by applying small amount of energy. So keeping this fundamental concept in mind, I can represent over here the bond enthalpy of Cl, two halogen atoms. You see 3 lone pair electrons are there, so less than compared to oxygen. The bond strength is more over here. Okay, lone pair 2, then it is less bond enthalpy than compared to nitrogen having 1 lone pair of electron. Okay, so more the lone pair, lesser will be the bond energy. Is that clear? Next, bond order you can also consider. Bond order, it depends upon bond strength. You can say bond strength. Bond strength means here you see C single bonds are there. Ethane, let's say CH3. This is a single bond. It is easy to break. So its bond enthalpy becomes minimum then compared to, I can write over here like C double bond C. Okay, the less than that of C triple bond C. Okay, so these are the factors on which the parameter, that is bond enthalpy or bond energy, depends. Okay, so next important parameter, that is bond angle. Bond angle, this one is nothing but angle, you know. So bond angle means it is the angle between two lines representing the direction of bonds. That means if I consider carbon dioxide, this one is a linear molecule, so here the bond angle is 180 degree. Okay, next methane, CH4 molecule, like this. Here this bond angle is 109 degree 28 minute. Okay, and next suppose I am considering ammonia. I have told you this one is lone pair, its shape is pyramidal. So here this NHH bond angle, that is 107 degree. Clear? Next, if I consider any molecules linear 180 degree, such tetrahedral, this one pyramidal, here this one is tetrahedral, this one is linear molecule. Okay, and this one is pyramidal, and another one, if I consider water, you see OH, two lone pairs like this, V shape or band shape. Here this is 104.5 degree. Okay, so here it is V shape or band shape, or you can say band shape. This is the concept of the parameters, that is bond angle. And next one, that is bond order. Bond order means number of bonds between the bonded atoms. Here you see, if I consider hydrogen molecule, so there is one bond, so its bond order is 1. That is 1. Oxygen molecule, 1 sigma 1 pi, so here you can say the bond order, that is 2. Nitrogen molecule, okay, 3 shared pairs are there, so you can say bond order 3. So more the bond order, bond strength will be more, bond enthalpy will be more. Okay, but bond length, that will be less. Okay, So bond order, these are the characteristics or parameters of some bond characters, you can say bond parameters. Okay, so in this class this is all about. So in next class we will discuss very important topic, that is hybridization. Okay, thank you.